Owing to some technical difficulties with the pen that I normally use, I will be recording the rest of the lecture for 3.1 using a PowerPoint type presentation. So the next topic that I wanted to look at is the idea of symmetry. We've seen a couple of graphs already that exhibit a certain symmetry. For instance, our x squared, our quadratic or squaring function, is symmetrical, as we would say, with respect to the y-axis. That is to say, if we were to flip it across the y-axis, if we grabbed the page at the two ends of the y-axis and spun it 180 degrees, the graph that we end up with will look exactly the same as the one that we started with. This type of function, one that is symmetrical in this way, is often called an even function. And the other type of symmetry that we'll look at is when a function is symmetric with respect to the origin. That is, if we were to put a pin in the origin and spin the page around 180 degrees, if the graph that we end up with looks the same as the one we started with, then we call that function odd. So here are a couple of graphs to consider. Here we have one that looks like our square function. Here we have one that looks like our cubing function. And here we have one that kind of looks like our cubing function, although it seems to have been moved around a little. So I would postulate that the first graph, the top left graph, is the graph of an even function. We can see that by flipping the blue curve across the y-axis, ending up with that dotted red curve, which happens to be in exactly the same place and overlap our blue curve completely. So this graph we would say is an even graph. Our second graph, I would put forward that this one is odd. We can see that by rotating that graph 90 degrees and then 90 more degrees, and we end up back where we started. So any function where we can do that, where we can put a pin right through the origin and spin the whole thing 180 degrees and get back to exactly what we had to begin with, is called an odd function. Now, not all functions are going to observe any symmetry. For instance, our third graph here is neither even nor odd. If I flip it horizontally, we can see that it's going to look different. It's going to be a decreasing function. And on the other hand, if we rotate about the origin, there we have our first step, and if we rotate the rest of the way, that would be our result. Now that does not overlap with the curve that we started with, and so this function has neither symmetry, and I would say it is neither even nor odd. Now something to notice about the even graph, here we have the point 1, 1, and on the other side we have the point negative 1, 1. Here we have 2, 4. On the other side we have negative 2, 4. Now that actually accounts for the evenness of this graph. If we plug in an x value, we get a y value. Say x and y is this point over here. If we plug in the negative version of that x value, if we came over that many units in the opposite direction, we would find another point at the same height. So 2, 4 and negative 2, 4, both lying at the same height, exactly the same distance from the y-axis. So that is algebraically how we're going to prove when functions are even. If we plug in negative x and we get the same thing as when we plug in x, then this is an even function. On the other hand, to determine when a function is odd, observe here that we have the point 1, 1, and if I go in the negative direction 1 unit, we find the point negative 1, negative 1. So if my x value gives me 1, its opposite gives me -1, gives me the opposite of the y value. And that is our test for oddness. If we plug in -x, we should get -y if the point xy is on the graph. So sometimes it's more convenient to determine whether a function is even or odd using its graph by analyzing it visually. So here we would like to determine if the square root function is even, odd, or neither. So let's see what that one looks like. Remember, that guy starts at 0, 0 and gently curves upward and off to the right from there, passing through 1, 1, 4, 2, 9, 3, and so on. So let me see how this thing looks if I reflect it across the y-axis, if I check to see if it's even first. Well, that's its mirror image, and that certainly does not look like the original graph. This is on the wrong side of the axis. It doesn't overlap what we started with. So this is not even. Let's see about odd. So let me put a pin right in the origin, and I'm going to spin this function around the origin, and I'll go counterclockwise. And there we go, and we end up with the red curve, which also does not overlap the blue curve that we started with. So neither one of the results of these tests for symmetry looks like our original function. They look similar, but they're not exactly the same thing. So this graph is neither even nor odd, and so the square root function has neither symmetry. Now we can test this algebraically. You have a test for this in your notes on the next page under the symmetry heading. Suppose we want to see if this function, -x squared plus 5x minus 1, is even, odd, or neither. Well, I don't know exactly what the graph of this looks like. I could put it in my calculator with relative ease. Let's see what it would look like to have a good idea. So -x squared plus 5x minus 1. There is our graph. Well, that does not look very even or odd to me. It's a little to the right of the y-axis, so it's not symmetrical that way. And if we spin it around, I think we would have a parabola opening upward, and that definitely would not overlap with what we've got. So my gut is telling me that this is neither. So let me put that away. Now, how do we test for this algebraically? Well, if I plug in 1, I would get some y value. If it's even, when I plug in -1, I should get the same y value. But that has to work for every single x value I could plug in. If I plug in 2, I'll get a y value. If I plug in -2, and this is even, I should get the same y value. Now I would be at that for a long time, but this is where the algebra comes in handy. If we plug -x in, just the general case, f of -x, we're going to see what we end up with. If we end up with our original function, if we end up with -x squared plus 5x minus 1, then this function is even. If we end up with negative f of x, that is, if we get the opposite of this, that would be positive x squared minus 5x plus 1, then this function is odd. So let's see what we come up with. Alright, so f of -x, we substitute a -x everywhere that we have an x in our original function. That leaves me with some simplification. Now I'll follow the order of operations, and this is where the order of operations becomes very important. You want to make sure that you don't miss anything here. The first thing that I want to do is simplify parentheses. Now, none of these quantities in parentheses can really be simplified, so my next move is to simplify the exponent. Now, if I square -x, that's the same as squaring the negative and squaring x. So this entire term, when I square it, is just going to give me x squared. I still have a negative floating around out here. This one is unaffected by the 2. by the power of 2. In that same move, I'll go ahead and multiply 5 times negative x, and this is my result. So f of negative x, if I plug in the opposite x value, this tells me about my output. Alright. Now, this is definitely not my original function. My original function has a plus 5x. This is also not the opposite of my original function. My original function, negative x squared plus 5x minus 1, its opposite would be x squared minus 5x plus 1. Everything would be flipped. Okay, and that is not the case either. So this is neither f of x nor negative f of x. In other words, when I plug in the opposite x value, I do not get the same y value, and I do not get the opposite of the y value that I would expect. So this function also has neither symmetry. It's neither even nor odd, and that is our algebraic test. So there in the notes you can find that approach. That's the one you're going to want to use whenever we ask for an algebraic justification for this type of thing. So the next topic in this section is pretty straightforward, but we do just mention it to keep it separate from something else that we'll talk about later. A global or absolute maximum of a function is the highest y value that it ever attains. And on the other end of things, the absolute minimum of a function is the lowest it ever goes. The lowest y value, the smallest, most negative, if necessary, y value. Now these two data are tied to the range of the function, right? The lowest it ever goes and the highest it ever goes, that's your absolute minimum and absolute maximum. Now these two words, absolute and global, they are interchangeable. You want to be very comfortable with those meaning exactly the same thing. Some texts call it one thing, some texts call it another. I tend to default to the word absolute, but I do try to mention both of them whenever I think of it. Now this is in contrast with the idea of a local maximum. Now a local maximum is basically the x value corresponding with the lowest point of your function. So there is a local maximum, or sorry, the highest point of your function. There is a local maximum at a point or at an x value a if every nearby x value does not make the function as big. On the other hand, the local minimum, that is going to take place at the lowest point in a neighborhood. And I use that word neighborhood, that is a common way of describing it. So some area where everything else is higher, the point that is the lowest is your local minimum. So I kind of like to think of this more informally in the notes. There are a couple of other wordings that you may prefer. A relative or local maximum of a function is the highest that it gets locally. So in a little neighborhood, if all of the points around that point are lower, then it is a local maximum. And on the other end of things, if all of the points in a neighborhood are higher than a point that you're looking at, that point is a local minimum. Now my favorite way of describing the local or relative maximum and minimum is as peaks and valleys. So wherever your function, as you read from left to right, has a peak, if you're going upwards and then you reach an apex, that is a local maximum. Now, if your function continues upwards from there, that's not a local maximum, because there's higher stuff nearby. But as long as it goes over a hill, that is a local maximum. And on the other side of things, the local minimum occurs anywhere you have a valley. So thinking of our function as a roller coaster, as you ride along it from left to right, you would have a local maximum at the top, and then ride your function down, and then if you come back up, right there at the bottom, that would be a local minimum. Now, the function may have many different local maximums, maxima and minima, but there will only ever be one global maximum, and there will only ever be one global minimum, if there is one, and I'll explain more about that in class. So looking at a graph, here we've got a fairly simple graph to analyze. We want to find the location of the local maximum, in other words, what x value gives us a maximum. And I see actually a couple of maxima. We have a peak right there at x equals 2, and then our function continues downward from there. Then we have another peak right up here at the top. Now, everything around this point is also lower than it, so this would also be considered a local maximum. So here we have one at x equals 2 and one at x equals 5. On the other side of things, we would like to find where there are local minima. Here we have a low point where our function is decreasing, and then it changes direction, starts increasing. We would say here we have a local minimum at 3, and we have one over here. This is also lower than all of the stuff nearby. If I drew a circle around it, this would be the lowest point in that circle. So this x value at x equals 1 also gives us a local minimum. Sorry, that should be minimum.